This is the third type of question in hypothesis testing, the kind that the standard deviation is unknown to us. So let's look at this question. The method is pretty much similar to the one before, the one where our number of samples was unknown. So I'll try to go a bit faster here because the steps is pretty much the same. So let's read the question first. In a factory that makes chocolate bars, the factory manager is concerned that the machine might be a little faulty and produces chocolate bars with lighter weights. Okay, that means he believes that the weight might be lesser. He decides to conduct a hypothesis test to verify his doubts. From the past records, the machine has been producing chocolate bars with mean weight of 70. Okay, so let's highlight this, mean weight. So this is like your population mean. Okay, and they are normally distributed. Okay, in general, when they tell you that it is normally distributed, there's a high chance that because later on they're going to conduct the test with a sample size that is small. Okay, that means we cannot use central limit theorem. But the fact that it is normally distributed, we can still conclude that the average, that means the distribution of the mean, will still be a normal distribution. Okay, this is a property of a normal distribution, right? Okay, so let me continue first. So we know the population mean, and they are normally distributed. So the manager randomly selected 20. Okay, you can see that the sample size now is just 20. Okay, which is considered a small sample size, right? Okay, he selected 20 chocolate bars to test. Their average weight is 68.5 grams. Okay, so this is your little x bar. So at 3% significance level, okay, the test concludes that there is sufficient evidence that the machine is producing chocolate bars with weight less than 70 grams. Okay, so we kind of rejected the null hypothesis here. That's given, and then we are supposed to find the range of possible values of the population standard deviation. Okay, so as always, we start by writing down what is our null hypothesis, okay, which is your H naught. Okay, in this case, your H naught, it claims, or okay, we can say it's claim. He's claiming that the mean was 70 grams. Okay, this was from before, right? So we assume that this is still correct. It is still 70 grams. Your alternative hypothesis, okay, thinks that now maybe because the machine is slightly faulty, it is less than 70 grams. Okay, and then step 2. Okay, I like to write down the random variable. Okay, let x be a random variable representing the weight of a random chocolate bar. Short form chocolate bar. Okay, and what do we know about x? We know that the mean of x, okay, which is the population mean, it's given as 70. Okay, but the variance is not given, right? But that's fine. We're just gonna use notation, okay, the sigma notation, okay, to represent the population standard deviation for now. So, of course, we are given that x is a normal distribution here. So the mean is 70, variance is sigma squared. Okay, and the test is being conducted by taking a sample size of 20. So what this means is that, again, the theoretical behavior that we expect to see is that, okay, the mean of these 20 samples, okay, which you can say it is just having x1 plus until x20. So each of the x represents a randomly chosen chocolate bar. So it plus, you divide to find what is the average weight. So we know that because individually, the x is already a normal distribution. So even if you plus, you divide by a constant, it will still be a normal distribution. Okay, so this is without using the without using the central limit theorem. Okay, because we know that it's already normal distribution, so that's fine. So our mean will still remain at 70. Okay, our standard deviation, our variance now will be sigma square, okay, which is the individual variance, divided by 20. Okay, so this is what I would expect to see that my result should behave like that. Okay, the result meaning the average of 20 samples. Alright, and then the next step, I'll write down what is the actual average weight that I got from actually conducting the test. Okay, so the actual test was given by the question. He says that the average was 68.5 gram. Okay, let me go out a bit so that you can read the question again. This one. Okay, the average weight is 68.5. So once I have these two information, the capital X bar and the little x bar, okay, I always like to draw my graph. So my graph, okay, I'll draw like that. Okay, x bar, it is a bell curve. Okay, the mean, it's given as 70. And 68.5, okay, which is this value here, we know that it is somewhere on the left hand side. Okay, so for now I'm not going to plot 68.5 first. Okay, I will mark out my critical region first. Okay, this is your 3% significance level, right? So this is your 3%. This is your critical region. Okay, so according to the question, the hypothesis test rejected the null hypothesis. So in other words, I can conclude that my 68.5, it should be somewhere here. Okay, 68.5. It is somewhere in the critical region. Okay, that's why we rejected, right? So this is what we know so far, and our job is to find what is the standard deviation. Okay, so right now it is hard for us to solve for the standard deviation because standard deviation affects the shape of your bell curve. Okay, it makes it skinnier, make it fatter, shorter, that kind of thing. So without knowing the shape, we cannot really find what is the sigma, okay, the standard deviation. But typically, okay, if you recall from the previous video, as long as you have a unknown in your one of the parameter, okay, we always change to the standard normal graph. Okay, this is just your normal distribution with mean 0 and 1. Okay, what it means is that the mean here, the 70, will become 0 now. Okay, and my critical region, the 3%, it will still remain 3%. Okay, which is this part over here. This is still 3%. Okay, the next thing that I want to find out is the 68.5. Okay, what does it become? Okay, this is actually the key steps. So this point here is what we call your test statistics. Okay, which we have a formula for that. It is simply taking x bar minus mu divided by your standard deviation over square root n. Alright, so let's just plug in all the values now. So x bar is 68.5, mu is 70. Okay, your standard deviation is unknown. Your n is 20 because they chose the sample size to be 20. Okay, so this expression here represents your test statistics. It is this point over here, this point. All right, then because we are supposed to find the range of values of sigma, right? The thing that helps us to find this range is the critical value, okay, which is this point. Okay, remember what's critical value? It is the point that marks the start of your critical region. So I need to know where is that point, right? So that I can conclude that the test statistics must be any point on the left of the critical value. Okay, that's the idea. So how do we find critical value? Okay, we just need to do inverse norm. Okay, because we have the area, right? So all I need to do is to make use of the area, inverse norm. Okay, the area is 0.03, that's 3%. And the mean and the standard deviation will be 0 and 1. Okay, because this is the Z graph, okay, the standard normal graph. Okay, if I do that, okay, let me use my calculator here. Okay, you go to second this thing, okay, the distribution, that one, inverse norm. Okay, you can see I have everything typed up. Okay, the area is 0.03, the mean is 0, standard deviation is 1. So I go down, paste, enter. Okay, it says that it's negative 1.88. Let me go back. Okay, negative 1.88. Alright, so you can see where this will be going now. Okay, I can start to form an inequality, right? Because we know that the test rejected the null hypothesis. So it means that my test statistics, which is this expression here, sigma over square root n, it must be less than negative 1.88. Okay, less than because it's a left tail test, right? So all I need to do is to solve for this. Oh, sorry, I should have written 20 here. Okay, all I need to do is to solve for sigma. Okay, so let me do it quickly. If I let me see what I can do. So I can take 68.5 minus 70, that's negative 1.5. It will be less than, this will be negative 1.88 times sigma divided by square root 20. Okay, so let me press calculator for this value over here. That will be, okay, this number here divided by, let me double check, square root 20. Yeah. Okay, square root is here. 20. Okay. So it's negative 0.42. Okay, so it will be negative 0.42 sigma. Let me check my decimal place again. Yeah, maybe I just include one more decimal place, 421. Okay, and to find sigma, I just divide by this constant throughout the inequality. So when I do that, let's not change too many things. So I'm dividing by a negative number, so the sign will change. It will look like that. If I divide, so I press my calculator now. 1.5. Okay, maybe I shouldn't press 1.5. Never mind. Divide by 0.421. Okay, 3.56. Okay, 3.56. Okay, so this is the answer. We have that the standard deviation, okay, the range of standard deviation is anything that's less than 3.56. Okay, so you can write it in terms of a set, okay, from negative infinity to 3.56. Alright, so that concludes our answer. Hopefully this helps you revise this chapter a bit more. Alright, see you in the next video.